nanohub.org.
Online simulation and more for nanotechnology.
All right, so if you join me for my my NanoHub U course in the fall, we'll probably have 3 lectures or so on this topic. So this is going to be pretty brief. But we ought to know a little bit more about electrostatics, because like I said, this is, when you ask why do all of these MOSFET theories work so well, it's because the device operates by electrostatics, manipulating potential energy barriers. Now, whether the transport over that barrier is drift diffusion or ballistic or quantum mechanical, that's sort of a detail, right? The important thing is the Poisson equation, right? So MOS electrostatics are really important. So, all right, so we've talked about the energy band diagram in the X direction. Let's talk about the energy band diagram in the Y direction, and we'll get a little more appreciation for MOS electrostatics. So here's a MOSFET. I've made the channel a little longer because we want to look in the normal direction, and I don't want to worry about two-dimensional effects. So we're going to be looking in the heart, right in the middle of the channel, where the electric fields from the source and the drain aren't affecting us very much. And we're going to look at the energy band diagram into the depth as we go from the surface into the depths of the silicon. Let me turn it around because I'm going to be plotting my energy band diagrams this way. Okay, and the goal is to understand, why does Qn equal minus Cox Vg minus Vt? Just to understand that a little bit. And we'd like to know, like, below threshold. What happens below threshold? Because that's an important problem too. Okay, so in the normal direction, we have this gate, and it has some Fermi level, so I'll call that EFM, Fermi level in the metal. And all the states below the Fermi level are filled in the metal. Then we have this thin insulating layer. And then we have a p-type semiconductor in the channel underneath. And if I had just the right metal and just the right doping in the silicon, all the Fermi levels would line up when I apply 0 voltage. And I would have these flat band conditions, and that would be a nice starting point. Now that'll never happen, right? The work function of the metal will be different than the work function of the semiconductor, and this won't happen. But all we'll have to do is to add a little correction at the end, a work function difference. So conceptually, this is an easier way to do it. Okay. Now, the question we're going to ask now then is, what happens when we apply a gate voltage? So when we apply a voltage to the gate, the voltage is just going to lower the Fermi level in the gate, pull the Fermi level down. Okay. So what I've described here is the conditions, the flat band conditions, and these are occurring at a voltage Vg prime equals 0. The prime is just to remind us that we're considering this hypothetical metal that has a work function just right to make sure that this happens at 0 bias. Otherwise, it happens like at minus 1 volt or at some finite. We just have to shift all the voltages. That's all. All right. So I apply a positive gate voltage. Boom! It pulls down the Fermi level in the gate. That positive potential in the gate then is reflected. It pulls down the energy bands in the oxide because potential is minus Q times voltage. And it penetrates into the semiconductor and pulls down all of the energy levels in the semiconductor and starts pulling the conduction band down near the Fermi level. So my energy band diagram looks like that. That's a positive gate voltage. Okay. Okay. And, you know, my conduction band is varying with position because the electrostatic potential is varying with position. So I can always define a reference, you know, potential. I can always make an arbitrary reference where my 0 is. Let me think about the 0 for potential being in the bulk of the semiconductor, deep into the silicon. I'll call that potential equals 0. And then when the bands bend down, the potential goes up. So the difference between the conduction band in the bulk and the conduction band at any location divided by charge, that's my electrostatic potential. So you can see when the energy band goes down, it means the electrostatic potential is going up because I applied a positive gate voltage. The closer I get to the gate, the more positive the potential is. Okay, so at any point there, I have an electrostatic potential that increases as I go towards the gate. All right, so there are a few things that I need to discuss. The semiconductor was doped p-type. And that means, you know, there's a relation. There are a lot of empty states in the valence band. And the density of holes is significant when the Fermi level is close to the valence band. But when I apply this positive gate voltage, I pull the bands down so that now the valence band is much further below the Fermi level. It means that most of the states are filled and there are much fewer holes. The other way to think about that is I'm applying a positive voltage or positive charge on the gate. That's repelling the positively charged holes in the semiconductor and pushing them away. So we say that the semiconductor surface is depleted of holes in that region where we bent the bands down. So we have a small number there, but we're left with the dopants. Those holes came because we doped it p-type with boron, and those dopants are negatively charged. So I'm left with a negative charge in that regime. And classic, electrostatic depletion layer theory, we can calculate the width of that region that's depleted. It goes as the square root of the potential at the surface and 1 over the square root of the doping density. Those are things we learned from basic semiconductor physics. The total amount of charge there is just the charge density. So minus Q times the density of dopants times the width of that region. That gives me the charge in coulombs per square centimeter. Okay. All right, but that's not the charge I want, because that charge can't give me any current for the MOSFET. That charge is fixed in the lattice. Those are the dopants that are just sitting there. The charge I want is the negative charge. I want the mobile charge. So as we're pulling the bands down we pull the conduction band, it gets closer and closer to the Fermi energy, meaning there's more and more probability that those states are occupied with mobile electrons. That's what gives me the charge in the inversion layer. So there's this exponential relationship. The higher the Fermi level is with respect to the conduction band, the more electrons there are. This is Maxwell-Boltzmann statistics, because it's easiest to do it this way. Not necessarily because it's accurate. If I want to be accurate, I'll do Fermi-Dirac statistics and I'll get Fermi-Dirac integrals, and it will just get a little more complicated. And we have a nice set of notes on the NanoHub about Fermi-Dirac integrals written by Rossong that I can refer you to. But we're going to do Maxwell-Boltzmann statistics today. So that's the electron density per cubic centimeter. What I want to do is to integrate that through the depth of that layer and get all of those electrons, because they can all flow from the source to the drain. That's going to be my charge in coulombs per square centimeter. That's the mobile charge that can give me current. Okay. Now, we can just write that down. Okay. We can do the mathematics, but here's the answer. Now, the electron density depends exponentially on the density depends exponentially on how close the conduction band is to the Fermi level. So there's some electron density in the bulk. It's p-type, but there are a few minority carrier electrons. That's n sub b. In fact, the number is ni squared over the doping density. Right? Very small number. If I bend the bands down near the bulk, I'm bending them down by the potential at the surface is psi sub s, the surface potential. That's how much closer the Fermi energy, the conduction band is to the Fermi energy. So the carrier density is exponentially increased by that factor. Okay, that's right at the surface. Now, as I go into the surface, the conduction band gets further and further away from the Fermi level. I get fewer and fewer electrons. If I want to account for all of the electrons, I have to, let's say that all of the electrons within a layer where the density drops to 1 over E of its value from the surface. Let's just count all of those. That means when the potential drops by kT over Q, the electron density will drop to 1 over E of its surface value, and then I have most of them. The thickness that it takes to do that is the voltage drop kT over Q divided by the electric field at the surface. Okay. So that's an expression, and you know, this is going to be a little fast for one lecture. As I warned you, if you want the full story, take my NanoHub U course, but you'll get the gist of it, and we can do this later. So let's look at what happens when we apply a big enough potential. How do we know when we've created a channel? Okay, well, I can look at when I have bent the bands such that the Fermi level is, well, let's start over again. Let's look in the bulk. The Fermi level is below the intrinsic level, or roughly the middle of the gap, by a certain amount. It's p-type because it's closer to the valence band. When I bend the bands such that at the surface, the Fermi level is above the intrinsic level by the same amount, then I have the number of electrons at the surface that's equal to the number of holes that was in the bulk. This we call the onset of inversion. We've made the surface as n-type as the bulk was p-type to begin with. So it's critical to know what that distance is in the bulk, that separation between the intrinsic level and the Fermi level, and if we divide by Q, we can just call that a voltage, psi sub B. And, you know, we have a hole density in the bulk that's n sub A, so we can compute that potential. If I know the doping in the bulk, I can compute that potential, and it's a few tenths of a volt, several tenths of a volt. Now, as I said, inversion occurs when we bend the bands by twice that number, so that the surface is as n-type as the bulk was p-type. So we just have to bend it down such that that surface band bending is equal to twice this parameter psi b. Okay. So then we can ask, what we're trying to do, figure out, is how the gate voltage affects the mobile charge that gives us the current. So the total charge in the semiconductor is two kinds. It's a depletion charge due to the dopants that's just fixed there, and it's the mobile charge that's been induced in the conduction band. They're both negative. So below threshold, most of the charge is a depletion charge because we have very few electrons in the conduction band. Okay. In that case, we just take our expression here. This is our expression, but it's an expression in terms of the surface potential, not in terms of the gate voltage. We don't know that. That's some potential inside the semiconductor device. Okay. So what we need to do is to relate that surface potential to the gate voltage. All right. So we have to determine how this mobile charge relates to the gate voltage. Now remember, I said below threshold, most of the charge is the fixed depletion charge. The inversion charge is small, but it's the only charge that gives us current. So this charge is still important because it gives us the leakage current, the current that flows below threshold. So we need to know it. Okay, so let's see. One way we can do that is to apply Kirchhoff's law. The voltage on the gate is dropped in two places. Some of it is dropped across the oxide, and some of it is dropped across the semiconductor. And we could use that, we could set up an equation, and we could relate the surface potential to the gate voltage, and we could get an expression. Okay, that mathematics turns out to be a little bit involved. So people, mostly when they're doing modeling, do it this way. Let's think about, we have the gate, we have the oxide, which gives us an oxide capacitance, but we also have a depletion layer in the silicon, which gives us a semiconductor capacitance, epsilon divided by the thickness of the semiconductor. So it's like we have two capacitors in series. And if I have two capacitors in series and I want the voltage between the middle of them, this is something we learn in elementary circuit analysis. It's voltage division. When you do voltage division by resistors, it's the bottom resistor divided by the sum of the two. When you do voltage division for capacitors, it's the top capacitor divided by the sum of the two. You just work out voltage division for that. And we can relate the surface potential is just given by Cox times Cox plus C depletion times the gate voltage. Or I'll write that as VGS divided by 1 plus Cox, C depletion divided by Cox. And that parameter occurs many times, so I'll call it M. It's just a numerical factor. Okay. And M is just 1 plus the ratio of those two capacitors. Okay. All right, so we're part of the way there. We can relate that mobile charge to the gate voltage just by that little expression. But I've still got an electric field at the surface of the semiconductor. And that's not something I know. So I have to relate that electric field at the surface of the semiconductor to the gate voltage too. So that takes a little more work. You know, so what I have in depletion, you know, I have some electric field at the surface. The Poisson equation tells me that it just drops linearly and goes to 0 at the edge of the depletion region depth. Gauss's law tells me that the displacement field at the surface is equal to the total charge in the semiconductor. The displacement at the field at the surface, displacement field at the surface is dielectric constant times the surface electric field. The total charge per square centimeter in the semiconductor is charge per cubic centimeter, Q times NA times width of the depletion layer. So if I do a little bit of work there, the surface electric field is just given by this expression, and you can see that I can write that as QNA over depletion layer capacitance, where the depletion layer capacitance is just epsilon in the silicon divided by width of the depletion region. Now, that depletion layer capacitance is somehow related to this factor M. So it means if I want that depletion layer capacitance, it's just M minus 1 times Cox. So I can plug that in my expression for electric field, and I get an expression that tells me what the electric field at the surface is. Okay, now we can go back. There's a little bit of algebra. You know, the first expression is one that I just wrote down by looking at the band bending. Okay, we got it in terms of the surface potential. The second expression we got from voltage division. It related the surface potential to the gate voltage. The third expression relates the electric field at the surface to the factor M and some other parameters. And I also have to remember that the electron concentration in the bulk p-type region with their minority carriers is Ni squared over Na. Okay, now I can put that all together into my expression, and I get something that looks like this, and I'm almost there. I have a factor Ni over Na quantity squared. And we might remember that that had some meaning to us. Ni over Na squared was related to this bulk potential. It told us the separation between the intrinsic level and the Fermi level in the bulk. So if I want Ni over Na, I can solve for it. And if I squared that, I would have Ni over Na squared is equal e to the minus q over 2 psi b over kt. Well, 2 psi b is the band bending at threshold. And the band bending at threshold is related to the voltage on the gate. It's just the threshold voltage divided by M. All right. So when I get all done with that whole story there, we've been looking at what the mobile charge is below threshold. And we've derived an expression that you'll find in most MOS books that tells us that the mobile charge goes exponentially with Vg minus Vt over this parameter mkt. We have an expression for it. So now we can improve the transistor model. We don't have to assume that the charge is 0 below threshold. It's finite, and that leakage current, we can treat it this way. Okay. Now, what about above threshold? We want to talk about this just a little more. Above threshold, we've written the charge as minus Cox Vg minus Vt. Okay. That means if I take the slope above there, the slope of that line should be Cox. It turns out that's not quite right. And we should look at that just a little bit so that we're aware of why that's not quite right. Okay, so let's look above threshold. So I bent the bands down enough to create an inversion layer. Now, if I apply a voltage to the gate, some of that voltage is dropped in the semiconductor. That's psi sub s, the surface potential in the semiconductor. Some of that voltage is dropped in the oxide. That's delta V ox. And then there's this shift V flat band for things like work function differences and things that I ignored at first. Okay. The volt drop across the oxide is just the electric field in the oxide times the thickness of the oxide. If I want the electric field in the oxide, I can just relate the displacement field at the oxide silicon interface to the total charge in the semiconductor. Gauss's law tells me that. Okay. So I have this expression that relates the gate voltage to the surface potential and to the charge in the semiconductor. Okay. Now the charge in the semiconductor is equal and opposite to the charge in the metal. If I apply a plus charge on the metal gate, I get a minus charge in the semiconductor. Those are my mobile electrons and depletion charge. And the charge has to balance. Okay. Now if I want the capacitance on the gate, capacitance is charge divided by voltage. So it's just going to be the derivative of the charge in the metal divided by the charge, but the derivative of the charge in the metal with respect to the gate voltage. That would be my definition of the gate capacitance. Or it's easier to work with 1 over the gate capacitance, which is dV. And now instead of the derivative with respect to Qm, I'll do a derivative with respect to minus charge in the semiconductor, because they're the same thing, and I know the charge in the semiconductor. Okay, so let's do that. If I just differentiate the first equation, I'll get a d psi s, d charge in the semiconductor, and when I differentiate the second term, I'll just get a 1 over C ox. So, charge divided by potential is capacitance. If it's a nonlinear capacitor, it's dq dV. I'm doing 1 over that. So that first term there looks like it's a capacitance. It's the capacitance of the semiconductor. It's the potential in the semiconductor divided by the charge in the semiconductor. So the charge on the gate is actually 1 over the semiconductor capacitance plus 1 over the oxide capacitance. So well above threshold, all of the charge is mobile charge. And that means the semiconductor capacitance is the capacitance of the semiconductor in inversion. Now, if I look at that, that means my total capacitance on the gate is equal to 1 over the semiconductor capacitance in inversion, if I'm looking at it above threshold, plus 1 over the oxide capacitance. So that's just a series combination of 2 capacitors. So that capacitance is always going to be a little less than the oxide capacitance. Right? So we weren't quite right with oxide capacitance. So let's recap here just a little bit. If I look at this expression of how the gate voltage divides with voltage division in these 2 capacitors, we had a semiconductor capacitance. Below threshold, that semiconductor capacitance is just epsilon divided by the width of the depletion region. Above threshold, you can think of that capacitance as being epsilon divided by the thickness of the inversion layer. Inversion layers are very thin. For many years, people said that's so thin that that capacitance is so big that when I put the 2 in series, all I get is the oxide capacitance, and you completely ignore it. With oxide thicknesses now being 1.1 nanometers, that's no longer the case. So the capacitance that we measure on the gate is significantly less than the oxide capacitance. This is actually a big problem for scaling. You want to improve transistor performance by thinning the oxide, but you don't get the improvement that you expect because of that. Okay, so the point of this lecture, and as I said, we're covering a lot of ground here in one lecture just so that you can generally appreciate what MOS Electrostatics is all about. If you take the course with me, we'll have about 3 lectures where we go over this and we can get comfortable with it. But the main points are that it is relatively straightforward to determine what the charge is below threshold. It goes exponentially with gate voltage. It may be small, but it increases exponentially. And that's an expression that people have been using for a long, long time. Above threshold, we just have to take the expression that we were using before, but we have to realize that the capacitance is the capacitance on the gate. That's what's inducing the charge. And that's a little less than the oxide capacitance. Right? Okay. So we have these expressions. Well below threshold, we have the expression. Well above threshold, we have the expression. It would be really nice if we had one expression that worked everywhere. And you can do that. And, you know, those of you that are used to modern transistor models know that most of them are based on a concept called a surface potential model. You can solve this, but it has to be done numerically. There's no analytical expression that will take you all the way there. You just solve the equations numerically. And most modern MOS models now are beginning to do that. There's also an empirical way that you can take some empirical function that automatically goes from one limit to another, sort of in the spirit of that FSAT function I talked about before. And that's an approach that in this virtual source model that's being developed by the MIT team, they use an empirical model that just smoothly goes between those two, and it introduces a couple of more parameters that you use to fit things properly. Okay. I warned you that I was covering a lot of ground. I'm going to cover a bit more, and then we're going to take a break. This is a two-dimensional problem. This is what makes it interesting and challenging. We sketched the energy band diagram in the X direction from source through the channel out the drain. I talked about what happens in the energy band diagram in the vertical direction, how you bend the bands down, you induce an inversion layer charge, how that's related to the gate voltage below and above threshold. But this is really a two-dimensional device. You can't really do them independently. You've got a two-dimensional field, you have to solve a two-dimensional Poisson equation, and that's very important from how transistors operate. Now, as I mentioned here briefly before, the goal of transistor design, what we mean by a well-tempered MOSFET, is one that has been designed so that 1D MOS electrostatics works at a point near the beginning of the channel that we call the virtual source. If you've done the electrostatic design really well, that works. That's what your goal is when you do electrostatic design. And that's why people are going to FinFETs and nanowires and things. It helps to wrap the gate all the way around the channel. And then we have this region under strong gate control, and we have that region under strong drain control. So this part of it, which part is controlled by the gate, which part is controlled by the drain, this all has to do with MOS electrostatics. And a way that you can think about this is that we've got this gate capacitor that is modulating the potential barrier. That's what we would like to happen. But we've also got a big drain voltage, and the drain is not that far away. And the drain field can also get over there and pull the barrier down. So it's like there's a capacitor connected between the drain and the top of the barrier. And it's a symmetrical device. There's actually one to the source too, and it's a 4-terminal device, so there's one to the bulk. So really, the task of an MOS transistor designer is to design the device such that the gate capacitance is the big one and the other capacitors are small ones and have a small influence on it. So you can see that the height of that energy barrier is going to be affected by, just do a little bit of circuit analysis on that, and you can see that it's going to be affected by those other capacitors too. All right. So here's some more simulations so you can see what a two-dimensional simulation does. This is high gate voltage, so you can see the conduction band in the channel has been pushed way down. And then as we increase the drain voltage, you can see that most of the potential drop is occurring near the drain, and you can see that things are more or less saturating near the source. You're not pulling them down more and more. So this is a well-designed transistor. All right. And you can look at a point where suddenly the electric field gets very strong because the slope there gets very steep. That's the pinch-off point of the transistor. All right. And this is what the velocities look like here also. All right. So the electron velocity gets very high in that pinch-off region, and the channel gets very small, but it's not really zero. Okay. Now, how do we design a transistor? So here's one way of looking at it. These, again, are numerical simulations. This is a particular device called a double-gate MOSFET. And what we're seeing here are the electric field lines. So those blue lines emanating out of the drain, those are the electric field lines. And you can see them coming out, and most of them are terminating in either the top gate or the bottom gate. But they're penetrating into the channel some distance. And that distance I'm going to call capital lambda. And we call that a geometric screening length. So most of you are probably familiar with a concept called Debye length, right? If you put a charge in a solution or in a semiconductor, the mobile charge moves around it and tries to cancel it out. And when you get a certain length away, most of this charge has been screened out and you're not aware that there's a charge there. That's called the screening length. That happens in bulk semiconductors or bulk solutions. But there's also a geometric screening length. So the field from the drain is being screened out by the geometry of the device. And if you design the device properly, you can prevent the field lines from penetrating into the device to the source, to the virtual source. That's what you would like to do. So the channel length has to be much longer than this geometric screening length, such that the source end is not affected by the electric fields at the drain. Then you have a good transistor. And that's why people are going away from traditional MOSFETs to structures where you try to wrap the gate around. So you get that double gate-like structure. You get a region of the channel that's strongly under the control of the gate, and the electric field lines from the drain can't penetrate in. Now, what you're trying to avoid here is something called barrier lowering. Remember, we showed you on IV characteristics what drain-induced barrier lowering looks like. You know, physically, what does drain-induced barrier lowering mean? Well, you have this energy band diagram, say under low VDS. What you would like to do is to pull the drain voltage high and not affect that barrier, because that barrier should be controlled by the gate. You don't want it to be controlled by the drain. That's undesirable. So this is a good device. If you built a device like that, you would see that the penetration of that drain electric field doesn't get to the top of the barrier, so it doesn't lower it, and only the gate controls that. So the current doesn't change. And if you plotted an IV characteristic at different drain voltages, you would see that things fall on top of each other, just the way they should. The threshold voltage is the same under low drain voltage and high drain voltage. But in any real device, you know, so we'd say that this device has no drain-induced barrier lowering. But in any real device, you're going to pull that barrier down by at least a little. And if it's not a very good device, you're going to pull it down by a lot. And as channel lengths get shorter and shorter and shorter and shorter, it gets really hard to avoid this. So what we've done now is we've lowered that barrier a little bit. If we've lowered that barrier a little bit, it's like lowering the threshold voltage, because now it takes less gate voltage to push it down to a point where we get a lot of current. So we've increased the amount of current that will flow through the device, or lowered its threshold voltage. So on an IV characteristic, you would have characteristics like the ones we discussed earlier. You would see that at a fixed gate voltage, you get more current at a higher drain voltage because you've lowered the barrier down. Or if you look at it the other way, to get the same current, you get the same current at a lower gate voltage when you apply a high drain voltage. So that's what we call DIBL. And, you know, drain-induced barrier lowering describes physically exactly the physics that's going on. Okay, so this is the longest lecture, and the other ones will hopefully be at a more comfortable pace, but we've got enough background now. I want to do one more sort of background talk, which will be on transport. And again, I teach an entire course on that. I want you to appreciate some things about drift diffusion, ballistic transport, velocity overshoot, quantum transport. Then we'll dive into the MOSFETs exactly. So what we've done here is we've summarized MOS Electrostatics, you know, sort of the highlights, gone through it very briefly, how to think about it under subthreshold conditions, how to think about it under above threshold conditions. We've mentioned this very important concept of geometric screening. This is what transistor design is all about these days. How do you design it so that your IV characteristics are, How do you design it so that it's a barrier-controlled device under control of the gate electrode only? And we've mentioned what drain-induced barrier lowering means. Okay, so time for a break, but let's stop and see if there's a question or two before we break, and then we will continue on this afternoon.